I think it would be good to start out this week reviewing what we know about muscles from last week, because we saw a lot of new material. So to get us up to speed, we had this relatively simple model of muscle where muscle fibers are oriented like this, and you've got the origin of the muscle up here and the insertion down here and tendon over here. And we said that the muscle works by essentially making this part slide back and forth. So as the fibers contract, this part would slide to the left, and then the fibers would get less angled. Right? They would become more like this versus like that. And these muscle fibers had some particular properties that had to do with their length and their velocity. So let's review those. And as a reminder, these properties come from experiments of getting a little bit of a muscle from a frog or a rabbit or something, and then just testing its mechanical properties, its force production capabilities, for example, in a variety of conditions. So we haven't really connected these properties yet to what the microscopic structure of the muscles will be. So if we look at the force that a muscle can produce as a function of its length, we saw a few things. Number one, if we're not activating a muscle at all, so if we just take a little sample of a muscle and we just pull on it, we find that there's this very familiar looking amount of force that comes up. This is very similar to what we saw with tendons, right? You pull on it a little bit and it starts stretching out. Of course, if the muscle is too short, you haven't gotten it out to its slack length yet, and so down here you would just get no force. So this is the passive force length curve for muscle. And we'll just keep this in the back of our minds. So when you're stretching out after a workout or when you're doing yoga, you're working against this passive property of muscle because you're presumably not activating your muscles when you're doing that. So that's not particularly interesting. What's more interesting is when we look at muscles' force production capabilities as a function of its length when the muscle's activated. So if we get our bit of frog muscle or whatever, we test it, its force production capabilities at a variety of lengths, we get this very characteristic curve like this. So there's this point about here where the muscle force production is at a maximum. And we have a name for that. We call that, I think in the notes, it's F naught for the maximum isometric force. It's isometric because the muscle's velocity is 0, meaning it's not moving anywhere. So it has the same length, isometric, same measurement. So this is the maximum isometric force. And of course, it's going to depend on the muscle, but we express the behavior over here and over here as just a percentage of that maximum muscle force. And one other thing that we do is we define whatever length it is, whatever muscle length produces this amount of force, we call that, the abbreviation in the notes is L naught, but it's just the optimal muscle fiber length. Sometimes people just say optimal fiber length. And it's optimal because that's the length at which we get maximum force. That's where it comes from. The passive curve starts going up right around that optimal length, but that is maybe more of a consequence of the fact that the maximum force is produced at this length, and the passive force starts ramping up there is related to some of the microscopic structure, which we'll see in one or two videos from now. But the thing to remember is that that optimal length is defined by whatever length it is that produces the maximum amount of force. Now, this plot right here is the active force length curve. And if you were to actually do an experiment, what you would get is something like this, which is because you also get this passive component added in, but then we just subtract it off to get what is the amount of force being produced by a muscle that we can attribute to the active contraction of muscle fibers. And it looks like this. You don't need to specifically know exactly these numbers, but it's useful to know that these limits here on the left and on the right happen to be at about 50% of the optimal length and about 50% less, 50% more than the optimal length. So that suggests that if your muscle length is, out here or out here, you can't produce any force at all. And then there was one more feature of muscles that we saw, which is the force of velocity relationship. So those plots we just looked at were for muscles that are not moving anywhere, meaning they have no velocity, isometric contraction. But if we generalize that to think about, say, maybe over here on the right, concentric muscle contractions, or eccentric muscle contractions, we see one more facet of muscles behavior. Now, a few things. We're going to measure force on this y-axis as a percentage of that optimal force that we just saw a minute ago. And we already know what we should get at 1.0 times the optimal force. We should get 1.0 on the curve, because this point right here is the same thing as this point right here. So what do we see? We see as the velocity of a muscle increases, as it's shortening more and more, the ability to produce force rapidly decreases. And there's something special about this point right here. It's the maximum shortening velocity. I usually abbreviate that V max. So that's the maximum speed at which your muscle can be contracting and produce any force whatsoever. Because once you get out beyond that, your force production capability goes down to 0. We also saw there's this strange, interesting, useful property where, let me move this out of the way, where when your muscles are contracting eccentrically, like when you're going down, like your quads when you are going down on a squat, for example, are contracting eccentrically, you're actually able to produce more force than your maximum isometric force production capability. And depending on the reference you look at, it's about 1.2 to 1.8x that maximum amount of force. So a little bit unclear exactly how much, but definitely more than your maximum isometric force production capability. And there was one more piece to this graph, which we saw was the power output. So from this, we derived one more graph, and the graph looked as follows. If you remember, I made this equation-based argument that we can express power as force times velocity, which means that at some point on this curve, we could think about power as being the area of this rectangle. So now I'm making the y-axis. The x-axis is still velocity, contraction velocity, but now the y-axis is power, muscle power output. You could also think of this as rate of energy production. So we saw that power has to be 0 when the velocity is 0 because that part's 0. And power also has to be 0 at Vmax because then this is 0. And so you get something that looks like this. Oops, something look like that, where the maximum amount of power, that corresponds to about 30 to 35% of Vmax. So to connect this to one other property of muscles, you're likely familiar with slow twitch versus fast twitch muscles. Slow twitch and fast twitch muscles have a different Vmax. So if this is a curve for a slow twitch muscle, maybe a fast twitch muscle would look like this maybe. So its Vmax would be higher, which suggests that the maximum power for a fast twitch muscle would occur at a greater absolute velocity. But it would still be 30 to 35% of Vmax. It's just that Vmax would be bigger for the fast twitch muscle, right? So it'd be something like this. So broadly, that is the details on what we covered last week. And in the next few videos, we'll start to build up some intuitions about a model for understanding where these properties come from and what the implications of the structure of that model might be.